last class, we started working on the topic of least squares fitting. And this class, we're going to continue working on the topic of least squares fitting. Last class, we actually wrote our own least squares fitting algorithm for a fit to a straight line. This class, we're going to focus on a SciPy user function for least squares fitting and fitting beyond a straight line. Last class, we looked at, as an example, fitting data on the expansion of the universe through measurements of the distances to galaxies and the recession velocities of the galaxies. Actually, some of today's class, we'll also look at that data on galaxy distances and galaxy recession velocities. So that's basically the plan. I just wanted to start with a little summary of a couple of slides summary of last class, and then I'll get on to the curve fitting that we'll do in today's class. I'm going to really work more than I usually do with the code today to get into the least squares fitting, and then I'll just kind of mention it, the physics topic towards the end, rather than start with the physics topic and go into the code later on. So this slide and the next slide are basically my summary of last Wednesday's class. If you remember, we talked about fitting the best straight line to some data points, and our definition of the best straight line was the straight line that minimized the chi-squared between the straight line and the data points, where the chi-squared was simply the sum of the squares of the residuals, or the differences between each data point and the fit function. And so that's how we quantified what we meant by the best straight line, is how we got the parameters of the best fit straight line. So if you're fitting a straight line to some data, so we called the data points xi, yi for the independent variable and the dependent variable respectively. The best fit parameters for the slope and the intercept, you could write out in this sort of matrix language here. So m is the slope, c is the intercept, and then over here on the right-hand side are summations involving the dependent and independent variables and products of those things. And then downstairs here's the corresponding uncertainties in the best fit slope, uncertainty in the best fit intercept, and the correlations between the slope and the intercept in this 2x2 matrix. And then that's written also in terms of the dependent and independent variables and the uncertainties on the data points. So sigma squared is the variance for the data points, square of the standard deviation for the data points. So that's one way we learn how to do analytically do a linear least squares fit. The way that we implemented it in the code was this fashion here. So we took advantage of Python and NumPy for some of the linear algebra that's available in Python and NumPy. And we saw that if we write our, this is basically writing our data, so the dependent and independent variables, and our model for the data, the straight line model for the data. If we write it in this fashion, so here's the independent variable, here's the dependent variable, we could write a vector that contains the best fit slope and intercept in this fashion here. So it's just this product involving these two quantities, and we could write the uncertainties and the correlations between the slope and the intercept in this fashion here, again involving the data and the uncertainties in the data. So that was the second way that we learned to write analytically the result of a straight line fit to the data. So both of those are kind of handy. Okay, so those work well for the case of a straight line fit to some data. But that sort of analytical way of calculating a fit to the data becomes more difficult in the sense it becomes messier, difficult, and actually more difficult in the sense it becomes very problematic or impossible for more complicated curves, more complicated functions. One of the reasons is you need to know the partial differential of the chi-squared with respect to the parameters of your curve. So we derive those equations by writing down the partial differential of the chi-squared with respect to the slope parameter, writing down the chi-squared with respect to the intercept parameter. It was easy for the straight line, but that might be more difficult for a different function, a different curve, or it might be impossible. You might not know analytically the differentials with respect to all the parameters for some particular curve, some particular function. So because of that, many times we solve the problem of finding the best fit curve to some set of data points, not by this sort of analytical approach that we've used of evaluating the differentials with respect to the parameters of the model, but rather a sort of numerical iterative approach to find the minimum chi-square and to find the best fit values for the parameters of your particular curve. And that's what curve fit does, and that's what many fitting packages do. And basically they use an approach to finding the minimum chi-squared, which is where the best fit values of the parameters are. They use an approach that we would call gradient descent. And so in gradient descent, there's sort of three steps in gradient descent. So conceptually three steps in gradient descent. So the first thing to do is imagine the kind of a landscape of chi-squared. So chi-squared, which is the difference, which square of the residuals, which is the difference between your function and your data points squared, is some sort of function of the parameters of the model. So in our straight line fit, it was some function of two parameters, slope and the intercept. If you're fitting a quadratic, it'd be some sort of function of three parameters. So it'd be in a three parameter space. In some other function, it might be more parameters. So firstly imagine chi-squared, the sort of chi-squared in this parameter space. So maybe just imagine two parameters, the slope and the intercept, and the chi-squared in that parameter space. So you could imagine kind of valleys and mountains of chi-squared, and you're going to try and find the minimum. You're going to find the minimum chi-squared because that's the location of the best fit parameters. And so one way of finding the minimum chi-squared, the best fit parameters, is just to start with some initial guess for the parameters. So you start with some initial guess for the parameters, the values of the parameters, and at that location in parameter space, what you're going to do is evaluate the slope of the chi-squared in that parameter space. So you evaluate that slope numerically. And you're going to take a step in that parameter space in the direction of the negative gradient, the negative slope. So that would start you walking down the chi-squared hill. So you take that step, and then you've taken that step, you're going to reevaluate the slope of the chi-squared in the parameter space, and then you're going to take another step. And then you'll reevaluate again at that new location, the slope of the chi-squared in the parameter space, and you'll take another step. And you just keep taking these steps until you reach a point, until you reach the location where you're in at the bottom of the valley of the chi-squared. That's where you know the rate of change of the chi-squared with respect to any parameter, the slope with respect to any parameter is 0. So that's the magic location of the minimum chi-squared and the best fit values of the function. So the third step is to recognize you've reached the minimum, the valley of the chi-squared, and that's where your best fit parameters are. So I kind of listed those 3 steps in this little paragraph here on the bottom left. And here's a picture that I stole of kind of imagining this trip from your initial guess way out here on the bottom left of the figure. We're just taking little steps inwards towards the minimum of the chi-squared by always walking in the direction of the negative gradient. And so that's how we find this location. And so we're now doing this numerically, we're doing this iteratively, rather than actually analytically knowing the differential of the chi-squared with respect to this parameter or that parameter. So this is sort of the analogy of this process that's always given. So you're on some mountainside, it's misty, you can't see, you want to get home to the valley, you want to get back to the pub or whatever in the valley. And so basically you start taking little steps, feeling your way. Where's downhill? So downhill's over here. So you take a little step in the direction of the negative gradient. And then I'll do it down here. I'm going to try and find out where it's downhill again. And so I take another little step here. And eventually you'll work your way down to the valley and be safe. And that's what the program is doing, it's taking these little baby steps through the parameter space of the chi-squared and walking its way down to the valley. So we're going to use this function curve fit that's in this package within this library, SciPy, to do our curve fitting. And on this slide, I just cut and paste the section from SciPy describing this function. So we could just look at, you know, the arguments that we give it. And so here's the most here's the most important arguments to this function. So one argument, the first argument you give it is actually the name of another function. And this other function is the function that you're trying to fit to the data. So this would be typically a little user function that you've written, your own user function, which might be a user function describing a straight line, or it might be describing a quadratic, or whatever model you have of the data. So this is the name of your user function that you want to fit to the data to get the best parameters for that fit to the data. Then the next two parameters here are a couple of arrays. So this array and this array are the dependent and independent variables. And then let me jump down here. This third array here, this is an optional array, which you don't have to use, but typically we would use this. It's the uncertainties on the dependent variable. And so with those arguments, you would call this function. And it's going to give you, it's going to return to you a couple of things. It's going to return to you a vector, an array that contains the best fit values of the parameters of your particular function, your model, and it's going to return to you a matrix that contains in the diagonals the variances or the squares of the standard deviations of those parameters, and on the off diagonals, it's going to have the correlations between those parameters. So that's kind of what our function from Wednesday's class was returning to us. It was returning a vector with the best fit values of the parameters and a matrix with the uncertainties and the correlations between the parameters.